All right, moving on here to problem number 5 on our practice exam. A little bit more going on here, so we have to hurry a little bit to get this one all in terms of the video time limit that I have to get things posted. So we want to calculate the pH again, but what we have now is a solution, and it's made by mixing two different solutions. We've got 25 mils of 2 molar formic acid and 50 mils of 1 molar potassium hydroxide. Now, you should know your strong acids and your strong bases by now, because that is how you know whether you're doing an equilibrium problem or a stoichiometry problem. Formic acid is a weak acid, but potassium hydroxide is a strong base. So these two will engage in a one-way reaction that we can calculate using stoichiometry. Now the trick here is that that reaction will lead to the formation of the conjugate base of the weak acid, which is itself a weak base. So the initial reaction we're looking at here is the formic acid, H2CO2. Now there's two hydrogens here. Only one is actually an acidic hydrogen. The other one is connected to the carbon, not to the oxygen. So the way this is written maybe is a little confusing. It could be HCO2H. That might be a little better, showing one hydrogen in a different position. But this is our acid. This is going to react, it's aqueous here as well, with potassium hydroxide, which hopefully you would recognize is a strong base. Strong bases only partake in one-way reactions. We don't have an equilibrium that goes along with a strong base. So the products of an acid-base reaction like this are going to be water, which is going to be a liquid, and so we're not going to have to worry about water changing the concentration. That's not enough to change our overall concentration. And then a salt of what's left over. So it'll be potassium of the conjugate base of formic acid, which would be formate. So our other product will be potassium. I'm going to write them separately because potassium is not going to have any effect on the pH. So what we're really going to have to be concerned about is this, which is formate. Although again, the name is not really important. It's got a negative charge. This is a weak base. So what we need to figure out here is, what's our solution going to look like after this initial acid-base reaction? Now, I usually call these if charts just to kind of contrast what's happening in an ice chart, because if it's a stoichiometric reaction, you can just calculate the initial conditions and the final conditions. So initially, we've got this sample of formic acid. Now, 25 mils, 2 molar. That's enough information for us to calculate moles, and that should be something that you could do in your sleep at this point. 25 mils, 1 liter is 1,000 milliliters, and the molarity is 2, so that's how many moles there are per liter, right? And that gives us how many moles of formic acid we have here. Right? And I would say you don't need to write this down. Right? Obviously, it's good to write it down if you make a mistake, because then I can look for what mistake you might have made. But I do think you should be able to do that without having to break a sweat here in the problem. Something similar for potassium hydroxide. Again, I'm just going to follow the same pattern there. It's 50 milliliters. Divide that by 1,000 to change it to liters, and then the concentration of the potassium hydroxide is just 1, so multiplying by 1. But it's 0.005 as well. So we have exactly the same in terms of the quantity of moles of our acid and our base. It's 1-to-1 in our equation. So this is a stoichiometric reaction. All of the acid and base are going to react. If all that reacts, that means in our final conditions, none of the reactants are left. All of the weak acid has been converted into conjugate base, so 0.005. And I should probably be a little more explicit here. This is how many moles, right? We can't use molarity when we're doing a stoichiometry reaction because that's relative to the solution. We need to calculate how many moles are actually reacting to see if it's a limiting reactant problem, or if it is stoichiometric like this one, to know how many moles are left over. So we have that many moles of the formate, weak base, produced here in the solution. The other thing we've got to factor in is that the volume is changing. We started with 25 milliliters. We added 50 milliliters of a different solution to it, so we now have a volume of 75 milliliters. So if I take the quantity of moles of formate and divide by how many liters my solution is, so again, 75 milliliters, I'm changing that to liters. That is something you ought to be able to do fairly efficiently now as well, so I don't feel like I need to write that one down. The concentration of formate is 0.667 molar. Now, we're kind of at the place now, or close to the place where we started the previous problem with the weak acid. We know the concentration of the weak base. Now, there is one other piece of information we'll have to figure out as we progress here, but let's move to the weak base equilibrium. If we have formate in solution, it's a weak base, it's going to react with water. That's going, weak bases remove H plus or protons from the water, so that's going to reform the weak acid as a product, and you take a hydrogen with a positive charge away from water and you get hydroxide ion. So there's our equilibrium in this case. Ice chart, 0.667 molar is what we start with, no products, so minus x plus x plus x, and by equilibrium 0.667 minus x, x, and x. Now, the other trick maybe to this problem, this is a base. This reaction is going to be governed by Kb, not by Ka. What we were given in the problem is Ka. So we have to calculate Kb here before we can determine if we can make this assumption and remove that minus x, so it's a little simpler to solve the problem. Now, in this case, we know, in any case, Ka times Kb is equal to Kw, since the acid and its conjugate base are related by the dissociation of water. Now, if we want to solve for Kb and we know Ka, we can just divide through by Ka. Kb will be equal to Kw over Ka. Kw is 1 times 10 to the minus 14th. We're given Ka for the weak acid, the formic acid in this case. And if we do that math, that will give us the value of Kb. Kb is 5.56 times 10 to the minus 11th. Right, now I kept one extra digit there. We're really limited to 2 by the original Ka, but let's minimize how much we round. Now, to determine whether we can ignore this minus x, again, it's the concentration, right, in this case of the weak base, divided by the K equilibrium constant, in this case Kb. So 0.667 divided by 5.56 times 10 to the minus 11th, right? And that's what we get, 1.19, or 1.2 times 10 to the 10th power. So that's 12 billion. That's a little higher than 1,000. So yes, this is a pretty good assumption. So it is greater than 12 billion. And it's not quite greater than 12 billion. I rounded it up, but maybe approximately 12 billion for that particular evaluation of the constant. So certainly good to remove that x. So take those values, plug them into the equilibrium constant expression. Kb is going to be equal to the products there, which will be x squared, over the reactant, which is 0.667 molar, right? And we just calculated Kb as 5.56 times 10 to the minus 11th. If we go through and solve for x there, so let me get the calculator on the screen because I'm not going to write it all down. 5.56 times 10 to the minus 11th. Multiply both sides by 0.667. Right, and that would be x squared is equal to this. So take the square root, and that will give us the value of x. So there's our value of x. X in this case is 6.09 times 10 to the minus 6th molar. Now back to our ice chart, we called the hydroxide ion concentration X, so that's equal to the hydroxide ion concentration. Now, just like pH is related to hydronium ion or H plus concentration, we can derive a concept called pOH, that is the negative log of the hydroxide ion concentration, and that's related to pH in a way we can use. So if I take just the negative log of my previous answer, so log and then change the sign, that's the pOH, 5.21. pH added to pOH is equal to 14, so if I subtract that number from 14, so on my calculator, I'm just subtracting 14. So I have a negative sign, but that's because I did it in the opposite order. That means the pH is 8.78 for this particular problem. And that's our final answer. Now, that can be a little tricky. Watch for that when you're using a weak base. You have this extra step. When you use a weak base, you'll get the hydroxide ion concentration out of the equilibrium constant instead of the hydronium or H3O plus concentration, and you'll need to go through this extra step to get back to pH. Everything's really defined in terms of pH, but sometimes the problem requires us to kind of work through the hydroxide ion concentration instead of the hydronium ion concentration. Okay, we'll stop there and we'll come back for problem number 6.